Hello everyone, my name is John Kraft. On this channel, I've done a couple of videos in the past on building a phased array beamformer, and then I also did a series of videos using the Pluto software-defined radio. But now I'd like to start a new series where we build our own radar and then use that to see a small drone. I'm going to start at the very beginning with very simple radar concepts that I'll first explain and then demonstrate, and then we'll grow that system step by step until we have a complete radar that can generate these very classical range Doppler plots. The end result is going to look something like this. Here I'm tracking an e-bike and a car, but in our final video, we'll be tracking a drone. I'll save that footage though for the grand finale of this series. But this video will give you an idea of what our end result will look like. It's a classic range Doppler plot where range is on the y-axis and velocity is on the x-axis. So each week I'm going to release a new video, and the video is going to have a few minutes of some radar concept, again starting with the very basics, and then we'll build that concept with real hardware. We'll program it with Python and we'll see it in action. So that'll be the general flow of each of the videos. If that sounds interesting, then you can subscribe to this channel and you'll see the new videos as they get added. But before we dig into that, let me first say two things. First, while I do work for Analog Devices on this channel, these are my own thoughts and opinions. I'm also not trying to sell you any Analog Devices items. If you want to build the stuff, and I really hope that you do, you can of course use whatever you want to do that. However, pretty much everything that I'm using is from Analog Devices because that's my day job and I know how to use all their stuff. So that's what's familiar to me. But feel free to use some other hardware or software if you are more familiar with that. Secondly, I'm not an expert in radar systems. This is an area that I want to learn, and I'm trying to figure out a few of the basics. And for me, it's easier to learn if I can see it working in front of me. That's why I'm doing this stuff. It's because I want to learn. It's not because I already know everything about radar. And if seeing how I build this also ends up helping you learn these concepts, then that's great. But please don't rely on my videos for the correct understanding of radar theory. There are a ton of great books and other YouTube channels out there that will be a far better treatment of that material. My contribution, I hope, through this video series will be how to apply some of those basic radar concepts into a real functioning system. And then from that, you can explore and learn whatever you want. And if you see a mistake that I'm making or something that could be improved on, please let me know in the comments. Then we can all learn together, and perhaps it's something that I can correct and implement in a new video. Okay, so again, in this video series, we're going to build a drone tracking radar system, and we'll do that in a step-by-step, a very easy to understand way. So that'll probably be like 5 or 6 videos. In the rest of this video right now, I want to talk about hardware selection. What hardware are we going to use to build up this radar system? It's a very important question, and I considered a couple different setups to use in this video series. So we'll get into that, and then why I decided to use the stuff that I ultimately ended up using. So that'll be this first video, introduction and hardware selection. In the next video, we'll start digging into radar concepts, starting with CW radar. And then we'll program our radar setup for that and see that working. In the third video, we'll introduce modulation into the transmit pattern. And that's when things really start to get exciting. We can do a lot of cool stuff with a modulating transmit waveform. Then in the fourth video, we'll do something called CFAR target identification. CFAR is a common means to deal with all the clutter we're going to end up with once we introduce modulation into the radar. Finally, in the fifth video, we'll be doing multi-chirp range Doppler radar. I'll take my radar outside and we'll look at cars and drones and people walking and all that kind of stuff. So that's the coolest of the projects, but I don't want to just jump right into that until we've laid the foundation for how we got there. And then after that, if there's interest, we could look at a bunch of other topics. But it can't just be any topic. The topics kind of have to be along the lines of things that I wanted to learn anyway. So as we get closer to the final video in this series, I'll put some possible topics in an online poll. And if there's enough interest in one or two of them, maybe I can do a video on them. So the kinds of topics I'm thinking about are things like we could redo all these experiments using MATLAB instead of Python. We could redo them all using just Pluto as our main radar vehicle. We could look at beamforming principles, and specifically as they apply to radar. So combining antenna pointing with radar. We could maybe even do something with a transmitting beamforming antenna. We could also look at modifications to our setup in order to increase the range. We could look at doing some more advanced clutter suppression and target identification kinds of algorithms. So, I mean, I don't know exactly, but it would be stuff like that. So I'll put a poll on my page, and then at the end of the series, we'll see where the votes stand. But also, please add your own ideas in the comments section, and I can add some of those ideas into the online poll as well. Okay, so it was a very long intro to kick off this video series. So now let's talk about hardware. And the first question is, what do we need our radar hardware to do? I mean, what are the key blocks that we need to incorporate? So let's start with a quick overview of the basics for really all radars. Radars use the transmission and reception of radio waves to determine the distance, velocity, and position of objects. A radar system will have a transmitter with an antenna and then a receiver with an antenna, and sometimes those are the same antenna. And then the received data and timing gets processed somehow, and that's really what the focus of future videos in this series is going to be. And thanks to the many advances in modern circuit integration, the actual hardware itself is not too difficult. The real challenges often lie in controlling the hardware, like timing synchronization, and then in processing the data, like target identification and clutter suppression. And there's two types of radar, and basically only two types. You either have pulsed or you have not pulsed. But we don't call it not pulsed, we call it CW for continuous wave. And you can see that the pulsed radar emits some pulse of RF energy and then waits for that to get reflected back, and that time difference is used to derive the distance and velocity. The CW radar is always emitting energy, and then it has to sort out the timing from all of that. There's many reasons why you would choose CW or pulse. Both are very commonly used and have very good applications. There's many great books and resources that go deeper into those differences. For our purposes, though, the key is that CW is always better at short-range radar systems. And to demonstrate these radar concepts, I don't want to have to go to a giant radar range or a big empty field. I prefer to work on them in my basement lab. So for this series, we'll do all of our labs with the CW stuff. So first, let's think about how we can make a simple radar. I've shown a pretty classic radar signal chain here, and this setup could be either pulsed or CW. It's pretty straightforward, but let's walk through it now. So we're going to start with some data. It could be modulated or it could just be a sine wave. For right now, let's just think of it as a sine wave. So we convert that data into an RF sine wave. This is done with a digital analog converter, also called a DAC. And then we amplify that sine wave, then upconvert it to some frequency. Now, this step is increasingly optional as data converters reach higher and higher RF frequency, but let's leave it in here for now as this is still the most common implementation. Then we're going to amplify that signal again. This is the PA or power amplifier of the radar. That signal goes out, it strikes some object, and then returns to the receive antenna. We have some LNA then to amplify that return signal. Then we downconvert that signal to get back to our original frequency and probably amplify it some more. And then we digitize the data. So that's what the simple signal chain looks like. Okay, so how could we build this up with real hardware and keeping it as simple and hopefully as low cost as possible? As I said, there were 4 hardware options that I considered. These were all radar systems that I've built in the past, and they all could work depending on what your goals and constraints are. I ultimately settled on the 4th option that we'll go over, but let me walk you through what the other options were and why I settled on option number 4. So first is option number 1, which is the very popular and incredibly clever MIT Lincoln Labs Cantenna radar system. I think many of you have already seen the system before. It's been around for about 14 years, and it's a great radar setup. I'll put this link in the video description. On this link, there are complete step-by-step instructions for how to build a 2.4 gigahertz FMCW radar system. You'll see the block diagram and step-by-step instructions on how to assemble it all, and even how to build the antennas. The reason it's called the Cantenna radar is that it uses metal coffee cans to create a directional antenna. And they walk you through exactly how to do that. It's very cool. And of course, there's very solid radar lectures behind all of this. So you'll get a great understanding of radar basics as you build up the hardware. And in fact, this is something that I built up several years ago. You can see my little coffee can antenna here. And this is my VCO ramp control timing board that they show you how to build on the little proto circuit here. There's also a great book by Gregory Charvot entitled Small and Short Range Radar Systems. The book is fantastic. It covers a lot of what was done in the Cantenna labs, but also provides some other setups and a lot of other great information and equations. I probably bought this book 5 or 6 times. It's a great book, so I lend it out to people. Then, of course, I never get it back, and so then I buy it again. It's a great resource, though, so check this out. So this MIT Cantenna Radar Lab is very cool. You can learn a lot, and it all works, and it's great. So why not use this for our radar labs here? The reason is that ultimately it's a bit of a dead end, and here's what I mean by that. The coffee can radar labs are fantastic. They work, the instruction behind them is solid, and you can do a lot with them. But ultimately, it's not what's done in the real world. I mean that it is super clever to use a sound card as a digitizer, but obviously nobody does that. It's just not scalable. Again, for putting together a system 14 years ago, this was absolute genius. But the technology and the integration level has changed monumentally since then. So it's just not the building blocks that a real radar system would use. And everything that I want to do on this channel is an overflow of what I do in my regular job. So in my regular job, I'm helping Analog Devices customers build massive phased array radar and comm systems, military radars, aerospace systems, LEO SATCOM phased arrays, stuff like that. So while we're definitely not going to do any of those things on this channel, I still want the building blocks to be the same. The idea is to start small and prototype with a low-cost, low-complexity system, and that's what we're going to do here. But then you can grow that system as your algorithm and your hardware demands grow. So even if you use new hardware and new software along that process, you don't have to start your prototyping environment completely over. Maybe you upgrade from the AD9361 to the ADRV 9009, or from the ADRV 9009 to the AD9081 or AD9084. But each of those steps builds on your previous hardware and software. You don't have to rip it all up, unlearn the old way, and then learn some new way or new software. It should all build one on top of the other. And so that's ultimately why I chose not to use the Cantenna material for this video series. I want something that could grow with your prototyping and final product demands. And so that brings us to our next option, which is to use Pluto. I've done several videos on Pluto. You may have heard me talk about it before. Pluto is our little software-defined radio built with the Cantenna transceiver family. By default, it has one transmit and one receive channel, but you can add a second receive and a second transmit channel if you open up the case and add these little U.FL to SMA cables. It can digitize or transmit RF signals from 70 megahertz to 6 gigahertz. And we can use Pluto pretty much out of the box to do some radar experiments. I'm showing here a picture of the MFCW radar that Victor Kai built. I'll put all the links in the description. And there's also a nice video from Dr. Don Metzger using the QIQ system software to implement radar with Pluto. It's using some interpolation and a pulse compression technique to plot distance versus time. So it does work pretty well, and I thought about using Pluto for all these labs. But the major limitation here is that Pluto can only digitize about 40 or 50 megahertz of instantaneous bandwidth. Technically, I think it's like 56 megahertz, but there's quite a bit of roll-off to get that, so really something more like 40 megahertz is more reasonable. And if you do the two-channel transmit-receive mode, then this reduces to 30.72 megahertz. And this limits our range resolution by quite a lot. I should point out that this option here, using Pluto for our radar, is the only option that doesn't use something called stretch LO processing. We'll talk about that more in later videos, but basically we inject the radar modulation into the LO of the transmit and receive mixers. This often gives us much greater bandwidth, even while using a lower data rate digitizer. However, the Pluto doesn't have an option to accommodate stretch processing, so we really are limited to 30.72 megahertz of bandwidth. But there's another option to still use Pluto and get great range resolution via stretch processing, and this is option number 3, using Pluto with external mixers. Okay, so how would we do that? Well, we'd first start with a Pluto. That will give us our ADC and DAC, and then we add mixers like these tiny low-power LTC 5548s. And those mixers are going to need an LO, and this is a really key part here. So if we choose something like the ADF 4159 PLL and then some VCO, then we can create whatever frequency that we want. And the ADF 4159 can program that frequency to execute a ramp, which is going to be really important later on. Then we'll use some amplifiers that are appropriate to our frequency range. These ADL 8107s work great for X and KU band. They have decent enough power handling to use as the first stage in a PA, and they're also low noise, so we can use them for the receive LNA as well. And then some antennas, and that's basically it. That's how we could build a higher bandwidth radar with Pluto. And this works really well. You can check out a video that I made actually in my garage several years ago, but it's basically this exact setup. And then Michael Henrik and I presented a much nicer version of this at GRCon 2022. So you can check out that video here. And you can even build all this up with the X-Microwave prototyping system. So it creates a very clean setup. And you could also cobble it together with eval boards. And this is actually a pretty compelling radar setup. It's at a pretty reasonable cost, but it can generate whatever frequency and bandwidth that you want. So for a while, I thought that this would be the setup that I use in these videos. However, I have an even better option, which will open up a lot of future possibilities for us, and that is Pluto plus mixers plus beamformer, which is all nicely put together into something we call the phaser. Okay, so what is the simplest way to add a beamformer into the option number 3 setup? Well, we'll again start with Pluto, and we'll put the mixers in there again, and the LO synthesizer. But now we'll insert a beamformer into the receive side of our signal chain. And for the beamformer, we can use this 8R1000 chip. It's an X-band half-duplex transmit-receive beamformer IC. And to keep it simple, let's just do beamforming on the receive side. So the transmit side will have one channel. And this isn't unusual in beamformers. Oftentimes, there will be many more receive channels than there will be transmit channels. Then for the amplifiers, we'll stick with the ADL 8107s. And then finally, we'll have the antennas. But our receive antennas have changed to an array of patch antennas, where each antenna goes to a separate channel on the beamforming IC. So that's it. That's how we could build an entire phased array radar that is very simple and fairly low cost. And that is what we put together with this phaser kit. I've done a separate video just on phaser, so I'll put that link in this video's description. You can check that out for more background information. But real quick, phaser is ADI's software-defined phased array radar educational and prototyping platform. As we saw, it's basically Pluto with a 10 gigahertz phased array front end. But you can do a lot more with phaser than you could do with Pluto, though all of the programming is actually going to be very similar. So phaser has 8 receive antennas, and those are in a linear configuration, and then it has 2 switch transmit channels. We use stretch processing to generate 500 megahertz LFM chirps. We'll talk more about that in the third video of this series. And the overall kit just gives us a ton of stuff that we can do for short-range radar experiments. There are some websites listed on this slide that will give you all of the getting started instruction, along with complete examples in Python and MATLAB. There's also unboxing videos, there's programming videos, there are lab videos, all kinds of stuff on those links, so please check those out. And I will say, I know that many of you are having trouble finding the phaser in stock, and that is because we are struggling to produce enough of them, but we are working towards providing a more consistent supply, and I should have an update on that soon. If you're having trouble in the meantime, please reach out to me on LinkedIn or leave a comment, and I can try to help you find one. Here's some more details on the phaser RF board. I'll highlight the receive side. So the receive patch antennas are built into the board, and then we use the ADL 8107s to amplify that signal. Then the 8R1000 we use for beamforming, and then the LTC 5548 mixers for the down conversion. Then for the LO, we have the ADF 4159 and a VCO. This will allow us to generate very wide bandwidth chirps, which we'll talk more about in future videos. And on the transmit side, we have a mixer and amps going out to 1 or 2 transmit ports. We have 2 ports that we can do MIMO virtual arrays, but we're not going to talk about that in this series, so just ignore that for now. So putting it all together, here's the signal flow for our radar setup. First, we'll program Pluto to generate a 2.2 gigahertz complex sine wave. That gets upconverted to 10 gigahertz with a mixer. Then that 10 gigahertz is output from phaser. It strikes some object and returns to our array. And let's just ignore the beamforming piece of this right now. So the array just passes the signal from the received antennas to the down converter. The down converter gives us 2.2 gigahertz plus or minus the frequency shift from the object. And then that's the waveform we'll process. But more about that processing in future videos. And this is what the setup will look like all put together. The link shown there is where I'll put all the files that we'll be using during this video series. And this is what the phaser board looks like. It's just this nice little contraption that mounts to a standard tripod thread. Okay, so a few final comments on this option number 4. In this video series, I don't intend to use the beamforming piece of phaser. At least for now, we're just going to ignore that. But then why did we go through the extra trouble of putting the beamformer into our setup? Why not just use option number 3? A couple of reasons. The primary reason is that I do eventually want to build on this video series and include beamforming with radar. So when I do that, it will simplify a lot of those videos if we just start with the standard setup now. And then when we add beamforming, we can do a lot of cool things like monopulse tracking, we can do null steering, maybe a little adaptive beamforming, we can sweep the radar beam, all that kind of stuff. The second reason is that I think it's better to start with a more complete example and then strip out what you don't need. But it would be harder to do it the other way, like if you wanted to add beamforming into a single channel radar. So when I do this video series using phaser, and then if you ultimately decide that you want to use some kind of lower cost system, maybe Pluto plus mixers, or maybe even just Pluto, you can easily get there with a few simple modifications to the programs that I'll show you. And in fact, in my other videos that I've already referenced, there is code included in them showing pretty much all you would have to do in order to do that. Okay, so I hope this video series sounds interesting to you. In the next video, I'll talk a little bit more about pulsed versus CW radar, and then we'll set up and program our phaser to be a CW radar, and then we'll see that in action. I'll share all those details and all that code with you. So if that sounds good, be sure to subscribe so that you'll see when the next videos are coming out. And thank you again for watching. And please leave any comments with any questions that you have on this.